Okay, thank you, Praise, for the nice introduction. I will say it's an honor and a privilege, and thank you very much for the invitation. As I always say, it is a privilege to always give a talk on the continent coming from there. Today, as you say, I'm from the Institute for Financial Maths at University of Liverpool, Financial and Actuarial Maths, and then still hold position at the African Institute for Mathematical Science, AIMS, Ghana. I will be presenting a recent work with Ludovic Tampi, who's a colleague and friend from Princeton University. This is a stochastic maximum principle for stochastic optimal control of SDE with measurable drift. Basically, what we're trying to do is to derive necessary and sufficient maximum principle for stochastic control when our system has some coefficient which are not non-smooth, I would say mainly merely bounded and measurable. And this is a work that was I think available on archive about a month and a half ago. So it's quite fresh. And then I welcome every comment. So I understand that the audience is not only made of mathematicians working in the area of stochastic control or in the area of stochastic analysis. So I will start my talk with some very basic notion of stochastic control so that people who have not encountered it get used to what we are going to do. So I'm going to start with a basic, very basic example in deterministic control, then a motivating example in the stochastic case, and then I will present our result, the difference, and maybe a sketch of the proof, at least for the necessary maximum principle. So as I said, this is my outline. I will start with some motivating example and the framework, the main result, and the sketch of the proof. So here I just assume that I have a production machine and a production planning problem. So this is what happened, for example, in industry, where you have a machine that will produce one type of good. And then the raw material are processed by the machine and the finished product are stored in a buffer, right? So the production rate here is U and the inventory level in the buffer is XT. So we want to control, for example, the inventory level in the buffer. And what happens? So U is the production rate. So if you are a company, this is what, or you are the firm, this is what you can control. You can control the production rate. You cannot control the demand because that doesn't depend on you, right? So this is what you can control. Now, if I say at time 0, I have an X0 as my inventory, and I have the production, the demand rate is ZT, then we have this relation, right? The inventory, the production rate minus demand. This is what we have. And what the company can control usually is this. And the demand is written like this, where A is the relative demand, can be seen as the relative demand. So the cost, usually, if you are the company owner, the goal is to reduce the cost of having the inventory in the production, the cost of producing whatever you're producing, right? So, and we have the cost function, which will be given by this, where P is a cost per unit of time. So when we have C is usually the cost and so on. So this is how our function looks like. This is how our cost function will look like. And here, for example, those who are not used to this type of problem, when C1 and C2 is positive, it would be like a cost, and when they're negative, they can be also a cost or penalty. So there will be the surplus here, the cost for the surplus, and the penalty for the backlog. This is what we have. And P is the cost per unit of production. And the goal is usually to minimize an objective function. So this is what the people will do. And of course, you can say that your machine has a highest production rate, and now you have to put in your constraint, right? So this is the maximum production rate, and this is the maximum inventory level, because you only have a room which is just this big, so it cannot be much more bigger. So you put your constraint, and then this is usually what you want to solve. So you want to discount the cost over a planning horizon, right? So you discount the cost over a planning horizon, and you want to minimize it. So this is usually what will typically happen, right, in the production planning. And then this U satisfying this will be a call, for example, an admissible control. And also you will often take this U such that this equation has a sense, right? If it's not well posed, then you cannot do anything. So you often choose U to make sure that that equation is well posed, and meaning you have U and Z, meaning that you have existence and uniqueness. And here you also assume that it satisfies this constraint. So this will be an admissible control. This is a nice example from the book of Young and Zhu. So I like this example because it gives us a little bit what for those who are not familiar with control problem, what a typical control problem in production planning is. So now let us assume, because I said stochastic maximum principle, usually if you want to solve this type of problem, you often use, strictly speaking, this will be a control problem with a factor, because this is a Z, which is another state in the state. You're controlling this, but you need to take care of this factor. So this is a factor in your control problem. This, we are not really interested into that. And to solve the control problem, there are many ways. People use duality, people will use stochastic maximum principle or dynamic programming. And I will use maximum principle, quadratic maximum principle, and dynamic programming. And I will be using maximum principle. And when I say stochastic, why stochastic? Because now I assume, for example, let's assume, for example, that the relative rate of demand is random, so that we perturb it with a noise. For example, we assume that AT is not deterministic. That is, AT is BRT. So you could write it like RT maybe plus a noise, right? So this is what you could have. So you have a BRT, you have BRT, noise, and BRT plus noise. This is just a very simple example. And what happened here is that, you see, when you do this, your system becomes a random system. And in stochastic differential or stochastic analysis, there are many ways of describing the noise. And usually, typically, physicists will say, white noise, which is understood by us by the derivative of what is called a Brownian motion. So we will use the Brownian motion to model the noise, basically, to model the randomness in the system, right? And this is where we go maybe from a stochastic deterministic system to a stochastic system. We could also assume that the production rates is also random, right? So basically you have randomness. So you can have many ways of transforming your system to go from a deterministic to a stochastic system. So another example that we are interested, for example, this one is one example of a paper by Balali, Mezardi, and Al. So what they consider here was this control problem where you have your objective functional or cost functional given by 4, and X, which was their system, the control system, was given by 5. So if you realize there is a U here, U is the control. You have B1 and B2. These are the drift, and then you have the sigma here, which is deterministic function, and BT here. BT is a Brownian motion. And for those who are not used, so this is a stochastic process with stationary and independent increment, and then which is also normally distributed, right? Which mean zero invariance T. If you take the Brownian motion, it's nowhere continuous almost everywhere, and it's nowhere differentiable. So it's a very a strange kind of process. So it's nowhere differentiable. So if you want a function which is nowhere differentiable, the Brownian motion, I know analysis would have many ones like Tagaki function, Weierstrass function. These functions are also examples of functions which are nowhere differentiable. So here we are interested in such a system. And since we have randomness here, we do no longer have just a normal control here with the F. We take the expected value because we have randomness. We only consider expectation. And we assume that U takes value in this set, A minus 1, 1. This is your set of constraints, and the control will be admissible if this 5 has a solution, and then the solution, and then U also lie here in the space A. So basically, what do I call a solution for a stochastic differential equation? I mean, we have the notion of strong and weak solution. And the strong means you will give me a probability, the filtered probability space, and then a Brownian motion, and I'll be able to find a process X, which will satisfy almost surely an integral equality. And usually that process F must be adapted to the filtration generated by the Brownian motion. Here, this is what they assume. G and F are even, bounded C1 function and their first order derivative, and are increasing on X bigger than 0. This is one thing. B1 as a function of X is odd, B2 also a function of X is either even or odd, and both functions are bounded in Lipschitz, and sigma is bounded, so the drift is bounded, right? And one good thing is that they could show that if you have that, they wanted to minimize this. So, and they could show that the following function here, I mean, they could show this result. It's a very general result. They could show that if U hat and X hat are an optimal pair, and then there exists an F tilde adapted process, adjoint PT satisfying this equation, and for which the maximum principle, that is the maximum for the Hamiltonian here of U, X hat, U hat, and P, it's equal to the max here. So usually the Hamiltonian, not usually, is defined by F of, so if I have, for example, H of S XP, because a sigma here doesn't depend on the control on X, so I simply have F of X. There's a U here, I forgot. UP equal F of S X U plus B, which is the drift, right, of S X U and then P. This is our Hamiltonian. And so if you have an optimal pair, then there exists an adjoint process for which we have the following maximum principle. So this is the necessary maximum principle. And this phi is a fundamental solution of this. It's often called the first variation process, or the derivative, some people will call it the flow, which is the derivative with respect to the initial condition. But what we should keep in mind is that this function, right, is differentiable almost everywhere. It's not an everywhere thing. So that was the novelty of this work, because usually people will work for on stochastic maximum principle, and assuming that their drift or their diffusion are at least once differentiable. So this was the novelty here. So they assumed that they only had Lipschitz continuity, globally Lipschitz continuity. I think that I have some questions. Can I maybe have a look? And should I answer now or praise? I don't know.
Up to you. It's up to you because of your time. You want to answer now?
Okay, instead of Brownian motion, yes, Yusuf, thank you. It's a particular case of Levy process, but I will not. We are not able to prove that we have the same result if we change with a Levy process, even if I took the variance gamma, because for the variance gamma, if I take bounded and measurable, I'm not sure I have the result. I don't even have the result, the existence result of my system. Okay. And so this is what they could show. If you assume that in this result, it was assumed that X was written this way. B and sigma were globally elliptic with linear growth. And then this B, Tx, and A as a function of U was continuous uniformly in Tx. And then the derivative is continuous in U uniformly in Tx. And it was shown in this case that this U described here, you will realize that in the example I show you, the sigma is a constant. Sorry, is the deterministic. It doesn't depend on xt. So they could show that this one was the control. So what do they have here? B and sigma are elliptic, linear growth, and they have this other condition. So what we will do is to take our B, sigma first, to be sigma t, just a deterministic function, sigma t, depending on t and not on xt. And we will weaken the condition on the drift. Even though we're weakening, we will also only consider some very specific type of drift and show that we still have a solution. So that's why I said here, what happened if B1 in the above example is only bounded and measurable? Let me go back to that example, for example, here. This is the example I have. We have this is our example. What happened if this B1 is bounded and measurable? In this case, the result given by Mezzardi and others, there was a lot of, in the 80s or 90s, I think they had a series of papers on maximum principle with non-smooth coefficient. So when B and non-smooth, they only meant B elliptic, globally elliptic in linear growth. So now the question is, when B1 is bounded and measurable, what do we have? Do we still have a similar result? So this is what we have. This, I'm just giving the framework in which we are working. So T here, it's our deterministic time horizon. Omega is a canonical space, because we were somehow using Malievan calculus to just show some of the things. And B is a canonical space, and then P was the Wiener measure, right? There's a probability of Wiener measure. And sigma is a d-dimensional vector, and this is how a B is defined. We assume that B is this way, of this form. You see the sigma here is just a vector, right? So we take a vector. And we want to solve the control problem 7, right? We want to have a say in the control problem 7. So want to maximize G alpha where it's given by this. The set A is a set of admissible control. So one will ask me, for example, admissible control usually means that your alpha will be progressive. Your system will have, this system or this equation 6 will have a unique strong solution, and then we will have a certain bound of the solution, a certain moment of the solution. So alpha, for example, you can choose alpha to show that that set is non-empty. You can choose alpha, somewhat of Malievan differentiable, to be Malievan differentiable. to the second moment of the Malyavan differentiability is finite and satisfies some integrability condition. And you could show that this solution, this equation has a unique strong solution. And this is what we assume also, that the f and g are continuously differentiable with bounded first derivative. That's not a problem. We can also kind of weaken this condition. And their linear growth, and alpha is this. And in addition, B is B1 plus B2. So I know someone will say, Olivier, you still use something very special. It's very special, but yes, I do. And the next thing is maybe to see what you can do if you take the product, because of course, if you can do B1 times B2 of this form, then you cover a bigger class. But even for B1 plus B2, this is not a straightforward task. And again, and also we can only work at the moment in one dimension, not more than one dimension. I'll come to that soon. And the set of admissible controls, as I said, is the alpha such that these are true, valid. So, and then I said that if alpha is Malyavan differentiable, you could have something. Of course, I say it's bounded, Borel measurable, B2 is bounded measurable, and continues with its second and third derivative with bounded variable with bounded derivative. And I would also mention that if I take B of linear growth in one dimension, I could still show the result, but it will be true for small time only, not all time, for small time. So this is the result. If we assume that the assumption behind are valid, then the flow phi t is well defined, and it holds that we have this maximum principles, like yes, I would say a variational directional derivative, if you want. And the adjoint process, which was the P in the previous case, is given by this one, whereas where phi is given by this. I know some of us or you were not used to. Youssef is there, so yes, he's one of the experts in local time calculus. This is the local time of the process X. I think I have the definition of the local time, and I would give the meaning of this. So what is the local time? If I ask someone in geography, what is the local time? If I was going to the Department of Geography, people would just say it's a time zone of an area. So I think with we had this thing with Praise. I sent him an email. Please, can you confirm that the 3 EAT is 2 is 12 in the UK? Because I wasn't sure. I thought it was 1 at some point, because it was showing EAT is exactly CAT, Central African Time, which was not the case. Therefore, it could be confused. It could be also, so not to be confused with this the local time. So the local time in stochastic analysis usually is a property that the diffusion process, for example, like the Brownian motion, doesn't have to be a diffusion because we have local time for process, so we're not automatically diffusion. And that characterizes the particle, the time a particle spends at the given level. So there are several definitions for the local time. The local time can be defined via the Ito-Tanaka formula, but here I took a definition of related to the level set as given by Paul Levy. Right? So what does it say? It says that if you consider the following level set, right, then this is the local time. This is like the time spent here. So it was shown that this is 0, P almost everywhere for omega. So this was shown. What does it mean? It simply means that the local time is an example of a measure which is singular to the Lebesgue measure. And Paul Levy introduced this and shown that this measure LTX, which measure this, is different from, and show that this limit converge and it's finite and it's not identically 0. And it call it the mesure du voisinage or local time. So, and as I said, other people will use the so-called Ito's-Tanaka formula to define the local time of a process. And if I was using the Ito's-Tanaka formula, it just says that if I take X to be a continuous semi-martingale, then the local time xt minus A is equal to x0 minus A plus the integral from 0 to t, the sine of xs minus A dx and plus lxta. So this will be the local time of x at A. So this is an example of definition. This is another one. This is a Tanaka-Meyer formula. So that's how some people also define the local time. So now what the nice thing about this integral respect to the local time is that if you check here, this first variation process, if you, let me go back to the work by Mezerdi and Balali and Mezerdi. This is the phi which was defined, right? Assume that our sigma is sigma t, so it doesn't depend on x. So it means that this bit will disappear, and I only have this. And in one dimension, what does it mean? It means that I can write it in one dimension, right? I can write it as an exponential form. So I will come here and write the phi of t of sx. So I will write the phi of ts has the integral exponential, sorry, of the integral from s to t of b prime of s xs u, for example, ds. So this is what you would write. But u, sorry, let me use r here, r dr, because u is a control, for example. Assume that we do not have a control. Yeah, there's a question. Okay, I'll come back to your question, Ross. Okay, if B1 is just integrable, I'll come back to that. Let me just think. So here, what the nice thing about this one is that if you are using, for example, let me write my B, because when I say B prime, the B was B1 plus B2. So I could write integral from S to T of B prime 1 of R dr times B prime of R B2 xr ur dr. And what happened here is that the beauty of the local time, usually if my x, right here, I will have a b prime. But the good thing is also, if my x, for example, is replaced by the Brownian motion. So in general, if my x is replaced by the Brownian motion, just as an example, then this r, if I check, is quadratic variation, right? So the nice thing is Natalie Eisenbaum showed that if I have a continuous semi-martingale, then the integral from 0 to t of the derivative of f respect to s xs and its quadratic variation is equal integral from 0 to t integral over r of f of s z lx dx dz ds dz. So what does it mean? It means that you have a derivative here, and then you can write it without the derivative. So this somehow enables you to send the derivative of the function elsewhere. But then it was not only this, she writes, it means that if you have your x here is the Brownian motion. For example, if you had, instead of x, you had a Brownian motion, then you can actually use the decomposition of the local time. So this is what you will use with respect to the Brownian motion. And that was the main, I would say, one of the main ingredients we use here, because we said, how do you take the prime there to the local time? And even when you have this local time, how do you do that? So how do you transform it? So what we did usually is to, because you want a convergence in a certain space, so we took the expected value. For example, I can say that this convergent L2, and we transform by Gaisano this X to a Brownian motion, and then we use the decomposition of this local time. That's what we mainly use here. So, and it was very important for us to use this decomposition. Okay. So you can write this if you had, for example, the integral from 0 to t, an integral over r, you can write it as your f, f of xz of L b, now are replaced by the Brownian motion ds dz, because one will say, what does it mean? How do you write it? So you can write it as if, as integral from 0 to t of f of s b x, starting at s, for example, dbs plus the integral cap t minus dt to t of f of cap t minus s b hat a, or b hat s, right, dws minus a certain, again, cap t minus t f of cap t minus s b hat s b hat s over t minus s ds, where w t is b hat t minus b cap t, right, plus the integral of b b hat s, I think, over t minus s, right? Yeah. So this is what you have. So what is important here is I can go from an expression like this, which might be difficult to estimate, to an expression like this, which is nice to estimate in a probability way. So as I said, this one is the local time space integral, and this is the normal integral. It's well defined. And we could also show the sufficient maximum principle. What happened? How do we show the necessary maximum principle? Our B is bounded and measurable. Our B1 is not smooth. So how do you do that? First thing we did was to approximate the B by a sequence of smooth function. And from that, we find that for each sequence of approximated function, we can always find an optimal control, alpha n, for example, alpha hat n. And then we will use the Ekelen maximum principle to conclude. So this is what we did. We first take the Bn. This is the approximating sequence. The B1n is what is causing difficulty. So that's what we approximate. The B2 is nice. We don't do anything because we took it nice, right? So if you had taken it Lipschitz also, somehow you would have had to approximate it, but it's nice and no problem. So we know that for this nice Bn, the xn is a nice, the solution exists, no need to do much. And now we have a sequence of approximating control here. The f and the g do not change, and we define this distance. So what happened is we could show that this gn minus G n alpha minus G alpha was less than epsilon. Sorry, there's no C here, when epsilon goes to 0. This is very important, but because when we show this, what does it mean? It means that we could, from here, we could show that we can find an alpha, right? We can find an alpha star, an alpha hat, such that we have, I think we can find an alpha hat such that you will be able to show that Jn of alpha hat is less than the infimum of Gn of alpha. You could find an alpha hat such that this is true, plus 2 epsilon n. And when we do this, this is alpha in A, it means that this is a kind of optimal control, and we could use now the Ekelen maximum principle. When you do this, you can use Ekelen maximum principle to show that there exists another control, because alpha hat n, we have an alpha hat. Now we say that there exists another control, alpha hat n, which is tied to Jn, and such that the distance that we have of alpha hat and alpha hat n is less than 2 epsilon to the power 1/2. And we have that the Gn alpha hat n thing is less than Gn alpha plus 2 epsilon to the power 1/2. This is 2 epsilon n. This is what we have, and the distance here. This is the Ekelen maximum principle, and therefore the control alpha hat n is optimal for the cost function G epsilon n, where G epsilon n is defined by this one. Right, so this is what you have. So it's optimal for this. And we can now use the Gateau differentiability to show that we have this B0. Of course, when we have this positive, and this means we have this H, one thing that is important is how do we get that Xn converges to X, Xn alpha n converges to X alpha. So this was one thing that was important. So how do you get X of maybe n alpha that converges to X? So this is something, because what do you do? So if you have Xn, yes?
So Oliver, you have another question inside the chart. There is another question inside the chart.
Let me just take it. I have a question with something. Oh, why not use Luzin theorem instead of here? Yes, if you use of course, Luzin theorem said that you can always approximate this function, right? Then you will want to do it for continuous function, and then in the end you will still need to find a certain bound. So for us is to get a bound here that will not depend on the derivative of your function, because maybe if I write for X alpha n, it could be clear, Jeff. Should I? But maybe you could think of Luzin. I know we use Luzin in one of the paper, but it's still before using Luzin theorem. The question is, how do you approximate? How do you find the bounds of your approximating sequence independently of their derivatives? This is mainly the task that we have to do. This is one of the main thing, because we want to show, for example, that this converges to this. how do we show it when our B, this is xn, right? This is xn. So this is B of t xn, Bn of t xn. For example, minus so you have the solution. You need to get that solution to converge somehow, or to find a right approximation if you have xn and alpha. So I don't think Luzin will enable to do this directly, because we still need to find the right bound. So how do we find the right C independent of n, and that such that our epsilon n goes to 0? So this is the main difficulty. So if I put alpha n and a certain alpha here, dt. Yeah, so we could not at least directly use Luzin for that. And for the integrability, Ross, I don't think it will work for now, because we still need to find a condition. What integrability condition you need to show that your SDE has a unique solution, right? So even if you take LPQ, you don't know what to do. Only LPQ, you don't really know how to deal with this local times part. I don't think it's just integrable or LPQ integrable without having a weak derivative. I don't know yet if that's possible. So I wanted to maybe show something on the level of maybe a difficulty for approximating having this difference. I'm just going to take one basic, one basic not example approximation, and let's see whether we can get that easily done, right? So I have the first variation process. I want to show that in L2, maybe if I have phi n of alpha n, or let's not go to phi n, let's just stop at x, and then let's see what happened if I only use x, right? I only use x. Let's see what happened. So I want to write my difference, maybe xn. So let's say that I have an alpha 1 here and alpha 2. So let's see what happened. So if I have this one, and xn is the bn, right, and the b2. So this means I have xn of t is the integral from 0 to t of b1 n of s x ns, sorry, and plus b2 of s, yeah, b2 of x, xn, s, and alpha. Okay, dt, since plus dbt, sigma t. And x2, x of t is equal to the integral from 0 to t of b of b1 of s, x, s, b2. So if I take this difference, then I have, I can show, if I use the fundamental theorem of calculus, that this difference, I think, is integral from 0 to t. I will add and remove some part, and the integral over from 0 to 1, right? And then I have a bx. This is the derivative with respect to the second variable. So I can write here the derivative of b1n, right, of s, and I will put lambda x1 alpha lambda, not alpha. I put a lambda, I put a lambda x1 x alpha. There's an alpha 1 and alpha 2, for example, alpha 1 plus 1 minus lambda x. This is xn, and this is x of alpha 2 t. These are tt. Right? So this is what I have in the first component here, plus B2. So there's no problem here when I do S and I put the same thing here. Why? Because, and I have an alpha 1, for example. My B2 is bounded with respect to the second derivative. And I have a d lambda and x1, xn alpha 1 minus x alpha 2. So we have this, and I have ds. This is just from the first fundamental theorem, and plus something. Then you have b1n and tx alpha 2 minus b1, and so it's s x alpha 2s again, ds. And I have the b2 as well. For the b2, there shouldn't be a problem. So let's see here. The question is, how do we do, even if I wanted to apply, I want to apply, because a linear, because this equation is a linear equation in one dimension, I can always write it as an exponential. So I have an integral with the difference, and I have this exponential and the dx b1n, right? So the difficulty is here because we have, even though we have b1n, the derivative, respect to n. So when n goes to infinity, I do not want my bound to depend on the derivative of b1 respect to n. So then I make use of local time. This is where it becomes a bit more interesting. This for this simple case, because you have to do it for the flow and the rest. So then you change only for this term, because you have this derivative. How do you make sure that the bound is independent of n? But how do we know that the bound, how do we make sure that the bound is independent? Because if I take my b1n, all bounded and measurable, and right, I can always show that this one is a CBN. I can show that this expected value, because of course, I take this, the convergence in the L2 norm, the variant, the second moment norm or the first moment norm. So this expected value is always less than this. Oh, and sorry. And this term, as you can see, because the Bn are uniformly bounded, I can write that as B. So it's independent on n. And therefore, I have this, can show that this is like this. So I take this sequence that converge, and I show that the limit somehow doesn't depend on n. So this is one of the difficulties, because we have to take a function, sorry, that is only bounded and measurable, and then we want to approximate the function. So we need to show here that in the end that xn converges to x and yn converges to y. And if we see the definition of yn, this is it. So this is our y. So I'll have an n and n. So alpha n converges to alpha. So we still need to show that this convergence holds. So these are the main difficulty, because we remove all regularity, but then we make use of the local time space integral in this specific step, and then the Gisanov transform to go from your process X to the Brownian motion and use the density of the Brownian motion to prove it. And yeah, so I think I will stop here. Thank you.